Recording is rolling. It is Tuesday, January 21st. Welcome back from 3-day weekend, which is always nice. All right, so Martin Luther King weekend we had. All right, so a bunch of you guys just turned in your rotational dynamics quiz, so I'm going to be grading those pretty soon. So what else today? Back on Friday, last time I saw you guys, I gave you guys a racquetball challenge. You guys remember, took this racquetball, put it at the top of an incline, let it roll down the incline, and then off the lab table, landed somewhere on the floor. Where's the ball going to land? Right, so you guys saw this. I did post the solution after school back on Friday, so I do want to walk you guys through that to walk you guys through the thought process. Okay, so I'll do that here pretty soon. Also, this morning I got this in my teacher mailbox. Actually, I was looking around at the teacher mailboxes. It looked like all the teachers got these. So maybe you see this possibly in some of your other classes. Sure. Right. So STEM Career Showcase. Guys, what does STEM stand for? There you go. Science, technology, engineering, and math. Sometimes I see an A thrown in there, like STEAM. What does the A stand for? Yeah, arts. There you go. If you ever see that too. But all right, so save the date. Thursday, January 30th. So not 2 days from now, but more like 9 days from now. If this interests you or you think it might be worth your time, 6 o'clock in the cafeteria. So Thursday, January 30th, 6 o'clock in the cafeteria. Learn to make the best of future engineering classes at Vieira. Connect with UCF, Boeing, Brevard Zoo, Collins Aerospace, and more. Got a bunch of logos down here. So there you go. So that is Thursday, 9 days from now, cafeteria, 6 o'clock. All right. So, of course, main thing today is Kahoot with rotational dynamics. A bunch of guys are hopped on already just before I hit record. Here, guys, a little bit of context. The schedule first couple weeks back has been a little bit weird for a few reasons. My AP students, I have a couple more days I need to do rotational dynamic stuff with them. I know how you guys turn the quiz today, so it's a little bit out of order how I normally do it, but it would take a few days before we get to our next topic, so I can keep all my classes on track. The next topic we're doing, by the way, is simple harmonic motion and waves. We're going to start Thursday, so 2 days from now, with a pendulum lab. So you guys got a pendulum lab 2 days from now? Let me say. All right, and the very last thing today, about last 5 minutes of class, I have a Vsauce video for you guys. Why don't any animals have wheels? So if you ever wondered that, look. All right, so before we get to the Kahoot, we'll walk you guys through this racquetball challenge solution. Okay, so remember what was going on Friday? Took this racquetball, let it roll down this incline. It was 200 centimeters up, so this L is 200 centimeters. Right, then it roll off and turned into a projectile. Where's it landing on the floor? And whoever got that won. All right, so you guys are trying to win. Where's the lane? What is X? Okay. So solve this in two parts. The first part is the ball rolls down the incline, okay, which I think I got some posters for that. Let me find here's a poster, right, for a ball rolling down an incline. Get its speed at the bottom. This is speed at the bottom. Okay. Now this solution is specific to a spherical shell, right? But if I change out with a different type of ball, it'd be something square root, something with a GH, but maybe 6 over 5 would be different numbers. Right? And then the second part is to solve with the projectile. And for that, you have to go way back to deep last semester for projectile puzzles. All right. Oh, before I start checking through the solution, I want you guys to see some things, see what I measured and whatnot. Right. So I know that this L is 200 centimeters. I gave that to you guys. Okay. You have to get the height of the lab table. You have to get that. Right? And then, now here's where it kind of depends what you want to measure, what you want to get. I measured this H2, and that's the only measurements I got. L, H1, and H2. You guys see that? You can get the whole thing from that. Well, and also Earth gravity matters also. Right? But you can get the whole thing just from those measurements. A lot of you guys probably took a protractor measuring this angle theta. Okay. In the solution, if you look through my solution over the weekend, I didn't actually get it from measuring theta, right? Because do you guys see it here? This is one of the things I want you guys to see, like forest for the trees, like what information do you have to solve anything? Do you guys see if you measured theta with the protractor, which you could have done, which was fine, could have done that way. It would actually be redundant with the information that's already here. Okay? Guys, how can you get theta from just H2 and L? Inverse sine, exactly. Yeah, also called arc sine. Yeah, right. So, let me skip way to the end. So a few pages down. If H2 is 21 centimeters and L is 200 centimeters, you guys got that? 21 and 200. Let's go back to here. You guys got calculators out? You guys got calculators? Right. I want you guys to do a calculation. Who's going to figure this out? H2 is 21 centimeters. L is 200 centimeters. Somebody tell me, what does theta come out to be? Somebody tell me that. A second. H2 is 21 centimeters. L is 200 centimeters. What does theta come out to be? Aha! Yeah, about 6 degrees. So I got here. So inverse sine 21 on 200. Yeah, basically 6 degrees, right? Which you may measure directly with a protractor, and that's okay too. You could gone about it that way. Different information you start with. Okay. So I'll treat that as a redundant variable, and I'll get this all in terms of H1, H2, and L and Earth gravity. All right, so the ball rolls down the incline. So there's two ways to solve this I showed you guys. I showed you a torque method and an energy method. Here's the energy method, which I think is easier. And actually, I did solve this just for a generic ball. Let me find the poster for that. Here it goes. Right. It's basically this poster. Guys, this poster right here is exactly what's right here. Throw in a couple middle steps to help round that out a bit. Right? But have it in terms of any generic ball I. You guys see this I right here? Because what kind of ball are we talking about? Are we talking about a solid sphere or a spherical shell? Those balls would roll differently. So what is this racquetball? Well, it's probably something between these two. I might start with the spherical shell. Okay, well, it's probably got a really thick skin. So maybe it's like if these were on a spectrum, like where would this ball land? Where would this ball land? I bet this would land probably closer to this orange ball, but maybe somewhere between, like on a spectrum. Okay. So I'm going to solve the solution for both of these and sort of open up a window of answers, right? And see how far. Right? All right. Ooh, guys, how about this? How about this? Suppose I roll down a solid ball and a perfectly spherical shell. Guys, which ball lands further away? Let me see show of hands. Let me repeat the question, then I want to see show of hands. Okay. So if I roll down a solid ball versus a spherical shell, which ball is going to land further away? The solid ball or the spherical shell? Show of hands. How many of you think the solid ball lands further away? Solid ball lands further away. Yeah. Oh, yeah. A bunch of you. Oh, yeah. You guys are right. You guys are right. That's the winner right there. Why? Guys, why would the solid ball land further away? Because which ball is rolling faster at the end of the incline? The solid ball. Because the solid ball has, less rotational inertia per unit mass. Okay. Or if I have, let me find my roll race. Here's my roll race. You guys remember the solid ball always beats the spherical shell? Okay, so, all right. It's going to be rolling faster, hence terms of projectile roll. All right, that's the first part of this. Right, so I got that. Got the linear speed. Now, guys, this is a linear speed. Don't forget also that there's this angle thrown in the mix, which gives you a velocity leaving the edge of the table. Okay, so next part is to go over to projectile physics. Projectiles. Okay, you guys remember these kinematic formulas that keep coming back over and over? Right, so much so that I've got this quarter page conveniently at arm's reach all the time. Okay, so if I look at this ball. Here, guys, I should say this. Guys, projectile, I got to consider vertical motion and horizontal motion. I'm going to consider vertical motion first because that'll give me a time constraint. Like how much time is this to projectile for? Once I have that time, I can figure out how far it goes horizontally, which will get the answer. Okay, so I need to get the time. How do I get the time? Okay, well, if you just, here, guys, everybody here, if you just drop the ball, or if you had it rolling perfectly horizontally off the edge, how could you simplify this first kinematic formula? You could get rid of which term? This V naught T bit, right? Here's the height of the lab table. Here's Earth gravity pull in for some time, sovereignty. Now, here's the tricky thing with this particular question, though, is that it does have an initial vertical component of velocity, as if you threw the ball straight down. You have to consider that. Okay, so you're trying to extract T out of this full expression, guys, which leads to a what? Guys, what's coming up next starts with a Q. Quadratic. Aha. So how much time it takes is quadratic. Okay. And it ends up working out like this. Except if you look at this V naught Y, really that's the full V sine theta. So you have to consider that too. So I rewrote the quadratic for time. I got this full expression right here. Okay. So here's how much time it takes. And again, this is for any ball because I have some generic I down here. All right. So next page. Okay. All right, now we're going in for the win. I had to turn this landscape to fit this. So x equal, so how far does it go horizontally? Well, that's the horizontal component of velocity, v cosine theta, times however much time. So bit by bit. This v, well, that's what we got from the rotational mechanics. Right? Again, this is for any ball. That's why I left the general I there. Okay? Cosine theta. Now, this one, I want to point this out with the geometry. Because if you go way back to the beginning, you guys see this triangle right here? Everybody getting a good look at this triangle? Does everybody see this triangle? Okay. Guys, if I say cosine theta, isn't that this bottom leg compared to this full hypotenuse? Okay. And you can tell me, guys, what is this bottom leg equal to? I'm covering up the answer. What is this bottom leg equal to in terms of L and H2? Can you guys do the Pythagorean theorem? Do a little reversal on that and solve for solve for what I'm covering up. Right? Pythagorean theorem, right? Okay. Here, it ends up being root of L squared minus H2 squared. Okay, so you do a little subtraction. You guys see that? Okay. And I'm making a point there because that's exactly what shows up right here for this cosine theta. You guys see this cosine theta is that square root divided by L? Right? You guys see that? Okay, like adjacent over hypotenuse. Okay. And then finally T, and here's the whole quadratic we got for solving that projectile for the for T, right? All right, put it all together. Again, here's all my measured values. I got the height of the lab table, the incline height, and the incline length. Notice I don't have theta on here because that would be redundant. You can get that out of this. Sure. Here's Earth gravity, that matters. Okay. I did this for a spherical shell and also for a solid ball. The mass and radius of the ball end up canceling out. It could have been part of your equation, but it wouldn't matter because it cancels out in the end. All right, so here's what I got. For a spherical shell, about 66 centimeters. For a solid ball, about 72 centimeters. Oh yeah, the solid ball would land further out, just like you guys said it would. Right? And the actual answer would be somewhere between the two. I tried it myself after school, and I got about 67 centimeters when I measured it, which is, yeah, it's right in that window. Yeah, here we go. So there's the solution, full solution. All right, you guys ready for Kahoot? All right, Kahoot time. Let's switch over to Kahoot. Oh, whoops. That's the wrong thing. Share screen too. Doing that. All right, ready to go. All right, so rotational mechanics, Kahoot. All right, torque. Oh. So force times lever arm, right? Force times lever arm. All right, let's take a look at this here. Ah, okay, so using a wrench, classic example. All right, so here's your lever arm, I'm calling R. Right, here's your force F. Okay. And guys, when I say cross product, that means you multiply what? The parallel or perpendicular components. Perpendicular, yeah. And that's what the sine theta is about. So here's your F sine theta, which is perpendicular to that R. Okay, all right. Let's check out. So 4 of you guys got that? What are these other ones? Guys, some of you guys picked the red one. What is mass times velocity called? What is that in physics? Huh? We're going to use character P to represent that. What does P stand for in physics? Momentum? Is it momentum mass times velocity? Right. Some of you guys picked the yellow one. Or actually, let me do the green one. It's force times time. What is force times time called? If you apply a force for a time interval, that gives you a like an impulse, which is a change in momentum. Right. So actually, the red one and the green one are the same units, right? Right. Momentum, impulse. Okay. All right, now let's do the yellow one. Momentum times radius is something, but it's not torque. Okay. It's here. It's this one right here. All right. So if I have momentum times radius, well, they'll give you an angular momentum. That's what that is. Okay, so not quite torque, it's angular momentum. All right. All right. So you guys good? But torque. Torque is R cross F, results in I times alpha if there's a net torque. All right. Yeah, points on the board. I got Luciana, Elise, Croissant, Smiley Face with glasses. It's easier to loosen a nut with a wrench if you. Oh, yeah, all the above. All the above. Right. So, say there's a stubborn nut rusted over, got the wrench on it. If you push harder with a larger force, yes, that'll help. If you extend the lever arm, right? If you use a longer wrench or you put a pipe on the handle so you effectively extend it, right? And also, if you make sure that you're pushing perpendicular, won't that also help maximize that cross product, or if you push perpendicular, because parallel does nothing. So I'm doing sine theta. Sine of 90 degrees gives you 100%. Yeah. Here, let me find a picture. Right, so you guys are thinking about that picture right there too, right? All right. I got Nathaniel, Luciana, Elise, Croissant, smiley face. Football is kicked through its center of gravity. The ball will. Yeah, move without tumbling or spinning. Put this out with a picture. All right, so here could be a football. Here's the center of gravity of the football. I call it center of mass. Okay, is if you kick it right through the center, right, then yeah, it should just it's going to look like a knuckleball, right? It's going to fly off without rotating. Because what if you kick it down here at the bottom? Okay, so center of mass is here. You kick it down here. It's going to cause it to rotate how? Probably counterclockwise, right? Versus what if you kick it up here? It's going to go which way? Like clockwise, right? Right. So it's got this. It's like inertia down here. Oh, okay, so got it. All right. All right, got Olivia, Luciana, Elise, Person, smiley face. Resistance an object has to changes in its rotational state of motion is called yeah, rotational inertia. Right. So resistance to change in motion in general is inertia. And if we're talking about a rotational sense, yeah, that's rotational inertia. Right? Isn't that you guys remember these two meter sticks passed around class a couple weeks back? Okay. So this one on the left, rotate back and forth, easy to change its state of motion. The one on the right, it could be the exact same mass, but distributed differently. It's really hard to change its state of motion. Easy to rotate, hard to rotate. Right. And then here's a whole table of values here. Right, so there's like different aggregate effects depending on how the mass is distributed. Okay? And then here's the sort of application of this is say wind a string around a turntable. Right? The more rotational inertia, maybe the less angular acceleration because it's more difficult to change the state of motion. All right. Yes, all those go with that one. Yeah, Alexander, Luciana, Elise, Croissant, on fire, smiley face. Which has more rotational inertia, a bike wheel like a hoop or a solid disc? Let's say same mass, same diameter, but it's more rotational inertia. Yeah, the wheel. I can tell you, or wait, maybe have you guys tell me by a factor of what? What number? Yeah, like half or two, depending on which way you go, right? Okay. Yeah, so the wheel is going to have double the rotational inertia of the disc. All right, so that's this right here. Okay, so we're comparing these two right here, right? Okay, here's your wheel on the left. Here's your solid cylinder on the right. Okay. Suppose they're the same mass and the same radial size, right? The trick with the cylinder is not all its mass is at the location R, right? Only a little bit of it is, and a lot of it's more like closer to this axis of rotation. Okay, these are all rotating about the defined axes that are on this table, right? Okay. Yeah, so it works out to be half. Like it has to be less. And if you run the calculus to get an exact solution, it ends up being half the rotational inertia. All right. All right. Got Luciana, Ian, Elise, Croissant, smiley face. Which has more rotational inertia? Okay, if you keep your legs straight versus if you run normally and tuck your legs in, you're moving your mass in closer to your center. Okay, so what I have for that, it kind of reminds me is Okay, you guys from the side skater. Actually, this one's going to show up later today, at least a couple times. Okay. So if you're running with your legs straight, that's like distribute your mass far out. It's kind of like the picture on the left. Okay. Versus if you run normally and tuck your legs in, you're at some points moving your mass closer to your own center of mass that looks more like the picture on the right. Okay. Okay. So yeah, so rotational inertia would be different. So some of them are squared. Yeah, maybe this one could be helpful too, right? Some of like that. All right. Any solid cylinder will roll down an incline with greater acceleration than a hollow cylinder if yeah, none of the above is necessary. Right. The mass and radial sizes end up canceling out in that puzzle. Kind of like the racquetball challenge, right? The solution I took you guys through earlier today. Right? The mass and radial size of the ball end up canceling out. It really matters like how that mass is distributed. So, like, so here we go. We've got all these really objects. Wait, what was racing? I guess was it these two racing? I don't know. But here's always the rank order racing. And again, it doesn't matter what the masses or radial sizes of these are. Right, the ring will always lose to everything else. Right, the bowling ball will always win against all these other objects. Right, this is a solid sphere. All right, solid cylinder, hollow cylinder. Okay, okay, okay. Because the hollow cylinder, its mass is distributed so far out, it has so much rotational inertia, it's hard to get it rolling. Once it is rolling, it's hard to stop. Right. When a gymnast moves from extended to a tucked position, ooh. Yeah, decreased rotational inertia. Okay. So you guys remember rotational inertia? Of course, we got the sum of them are squared. Now your mass wouldn't be changing, but maybe how you distribute that mass. So if you go from extended to tucked, right? Yeah, you're going to decrease your rotational inertia. Okay. Now there's maybe some other things that come into play too, right? What happens to angular velocity, angular momentum? I think it's the next question now. Okay. Is everybody okay so far? It's good. All right. Let's see if it is. I think it is. Isabel, Zach, Elise, croissant, smiley face. Ooh, keep a slim lead. Oh, here we go. Ice skater pulls in his hands to turn faster. Uh, yeah. Oh, nice. Look at you guys go. Yeah. So angular momentum is conserved. There's the guiding principle there. Rotational inertia decreases, so angular speed increases. So all those are true. Okay. Actually, I got another question too. So here we go. So it's exactly right here. So here's the guiding principle. Angular momentum is conserved. Angular momentum is I times omega. I decreases. Omega is forced to increase. Just fantastic. Okay. How about this? Oh, guys, which picture? The picture on the left or the picture on the right? Is there more rotational kinetic energy? Let me see. Show hands. More, or let me give you guys a formula too. Guys, what's the formula for rotational kinetic energy? Just to compare that to L equals I omega, right? So you guys see that these two concepts, kinetic energy and momentum, angular momentum, they have the same ingredients, right? I and omega, it's the same ingredients, but we're doing different things with those, right? So no, picture on the left, picture on the right. Is it the same angular momentum? Yeah, that's the guiding principle. You guys just said that on Kahoot anyway. It's the same I times omega. It's the same. Okay? Let's run some numbers. What if it was like, how about 10 units times 2 units? Could that be 20 units? Okay. But what if you shrunk I down to like 5, like half as much? What would omega be forced to be? Huh? 4. Yeah, because that would also be 20. So angular momentum is conserved. Okay. Now what happens to this formula up here? So I'll do K original and K final. Maybe this is L original and L final. I know I'm dropping the units. I'm just trying to make this make the numbers pop out, right? Right. So I got 1/2 I, because I just copied that I, times this omega squared. Guys, what's 2 squared? Divided by 2 times 10, 20. So, and that would be like joules. I didn't mean that everything come out to 20, but it's just coincidental. All right, so like 20 joules. Can you guys imagine 20 joules? Right. I'll put a little J for joules. Right. Right. Now, what about the news? So I got half the rotational inertia, double the angular velocity, bring it up from 2 to 4. That gets squared. Guys, what's 4 squared? Divided by 2 times 5. Ooh. Right? Do you guys see the answer now? So which picture, left or right, has more rotational kinetic energy? The one on the right. The one on the right. Okay. Same angular momentum, but the kinetic energy increases. Okay. Guys, where did that energy come from? Does it come from, like, guys, if you're spinning, does it take some effort to pull your hands in? Yeah, it comes from your muscles, right? That's where that comes from. Okay. All right. Remember that. We're doing Nathaniel, Zach, Elise, smiley face, croissant. Large rotating cloud in space shrinks in size. It rotates. Faster, rotates faster. All right, everybody went in. Ooh, yeah. So, guys, isn't that the same question as this? Right, so you got a nebula in deep space. It's just a bunch of like dust particles, like maybe slowly rotating around, and they're also gravitationally attracting, which makes them turn from the picture on the left to the picture on the right. And then the whole thing's going to speed up spinning. Angular momentum is conserved. There you go. Yeah, I guess you could say gravity force is doing work, right? So that'd be a more kinetic energy also, wouldn't it? All right, Isabel, Zach, Elise, smiley face, croissant. One person leans toward the center of a seesaw. That person's end will. Seesaw. Yes, should rise. Should rise. I'm gonna grab my notes from earlier today. Right. So let's say we started off with a couple of friends. Let's say it's pretty well balanced, right? I got 2 friends, seesaw, balanced. Okay. You see relative to this pivot point in the center, the guy on the left causes counterclockwise torque, guy on the right clockwise torque. So bounce that. Now, if the guy on the left, let's say, leans in towards the right. Okay. Now, lean in, that's an incremental change. If you want to make it more obvious, what if you just like walk significantly towards the center? Right? Maybe that makes the answer, I mean, it'd be the same answer. It would just be more obvious. So I'm going to really make this guy walking towards the center. You guys see it, this radial distance shrunk down really small? And since torque is R cross F, that's a lot less torque than before. Well, a lot less counterclockwise torque. Okay, so now this whole thing goes, turns clockwise, doesn't it? Okay, hence the guy on the left, isn't it, is going to rise. Yeah, that's the answer. All right, Alexander, Nathaniel, Zach, smiley face, croissant. To turn a stubborn screw, it's best to use a screwdriver. Oh, this is a screwdriver, not a wrench. This is a screwdriver, not a wrench. A little different. Okay, so because the answer would have been long handle for a wrench, but it's a wide handle for a screwdriver. And so here's my picture. So still my notes from earlier today. Here's a wrench. Here's a screwdriver. You guys see that? Okay. Now the wrench, yeah, you definitely want a long handle on a wrench. That's true. Okay. But the screwdriver is, don't you grab this around the handle like this? And then this force here is, it's really a friction force between the handle and your hand, isn't it? Right. Okay. And then cross with this R, which it's that. Okay, that's the radial width of the handle. Okay. So that's where the torque is coming from. Is this R across this F. So if you have a wider handle, that would give you more torque, wouldn't it? Okay, more torque. Yeah, that would help you out that way. Okay. Or here, guys, what about this? What if I had a big old crossbar on this thing? What if I throw a big old crossbar right here, right? And I like, grab onto the crossbars. Now I'm getting a ton of torque, right? Now it's really easy to turn the screw. Yeah, look at that. Look at that. Alexander, Nathaniel, Zach, smiley face, horizontal. Ring and the disc roll down the hill together, which reaches the bottom first. Yeah, disc. Okay. Because well, if you make it really easy, if they have the same mass and the same radius, which has more rotational inertia, the ring. Okay. Okay. So define. Here we go. This right here. Okay. So here's the ring versus the disc. Right. So equal mass and equal radius, the ring would have more rotational inertia. It's harder to get rolling, so it's always going to lag behind and lose the race. Okay. Then of course you guys know. Well, turns out it doesn't even matter what the mass or radial size are. Okay. It just matters how the shapes are. Right. So how that mass is distributed. All right. Yeah. So the ring will always lose that race. All right. Elise, Nathaniel, Zach, smiley face. Croissant. Good explanation for why a ball gains speed as it rolls down an incline. Ooh. Oh, nice. All right. All right. So, do want to admit, I don't think this is the best worded question on this Kahoot, but yeah, okay, I'll do that. Those are all factors. Okay, and at least I can point this out on the poster. So, you guys remember ball rolling down an incline? I gave you guys two perspectives on this. Okay, so I normally default to the energy perspective because it's easier to solve the thing. But here's the torque perspective, which is kind of more how that question is framed. Okay, so what gets this ball rolling in terms of torque? Of course, they gave the same answer in the end. Okay, in terms of torque, though. Because if you have torque on something, do you need at least two different forces at two different locations acting on the object? Yeah, right, to cause a torque. Okay. So here I see three forces on the ball. Now this normal force I don't think really causes a torque, so I can sort of ignore that. Right. But this weight and this friction force, you need both of them to cause a torque. Because what if this? Because what if this surface was frictionless, like an air hockey table? You put the ball on it. Let's say there's enough force from the jets to keep it sort of afloat a little bit. Would this ball even roll at all? Or would it go down like a knuckleball? Yeah, I don't think this ball would even roll if there wasn't a friction force. Okay, so there has to be a static friction force to induce rolling. That's why, you guys see on this roll race, I put a coefficient of static friction here. Well, it's really between those surfaces, but whatever. Right? And I only gave one frictionless lane, and that's the air hockey puck. It's not rolling at all. Right? But if you want to induce rolling, you have to have a friction, like some kind of static friction here. Right. All right. So yes, we got that. That's going to result in a torque. Right. So this torque, okay, that's here's your torque. It's R cross F. So it's mgr sine theta is how it works out. Okay. That results in I alpha, and then you can work it out from there. Okay. So we got all of that going on. So we got the forces acting on it. There's a static friction, therefore there's a torque. So all the above. I was playing. Elise, Nathaniel, Zach, smiley face. Horizontal. At different orientations, the cams provide different. Okay, walk you guys through this because the picture's going to disappear in like 15 seconds. Could you guys imagine as you pull on this rope on the right, and this thing is rotating about this central point, it's getting all wonkety, right? So this effective radial distance is changing, right? You guys can see that, right? All right, so different orientations, cams provide different, yeah, okay, so the lever arms would be always changing for that cam, right? It's always changing, right? Now, if you provided a constant force, that would result in different torques. And then what this blue answer is saying is that if you wanted somehow some constant torque, which would be kind of hard to achieve, the only way to do that is you'd have to be applying a different force because that radial arm is always changing. All right, yeah, so that's why it's both of the above. All right, Elise, Nathaniel, Zach, smiling face, croissant. Ooh, spool time. I go to school. I learned about the spool. All right, so I should have said if you're on the left side and you're pulling towards the left, let's go to the left towards you. All right, let's check that because I got this right here, right? Got the spool, string. I see string wound around. So, right. Okay, so you know what I should put on the picture too is the table surface. I really should put that. So I got table surface here. So if I pull to the left, does it go to the left? Yeah, sure does. Look at that. Go left, pull to the left. Okay. Here, I'm going to tell you guys what the next question is. Is what if I dunk this whole thing upside down? You guys see, so the string is down here now. Right. Now there's also the table surface. That matters too. There's some static friction right here. Static friction. Okay. Because if I pull the string this way to the left, now it goes which way? Ooh. Oh, that's the next question. See if you guys remember this from last week. So, oh, got Peyton, Nathaniel, Zach, smiley face. Oh, salt. Running away. Pull the string, the spool will move. Let's gonna get this. Remember, there's a floor down at the bottom. The floor down there. Ooh, got a couple winners. Couple winners right there. Okay. I'm gonna show you guys that this is true. So also go to the left. Okay. So let's do the actual science first. Okay. So you got it just like the picture, right? You guys see just like the picture? If I pull to the left, which way does it go? Oh, to the left. Look at that. It goes counterclockwise to the left. Okay. Now why counterclockwise to the left? Huh. So I got it's from earlier today. Okay. So here's my spool. Right. Outside diameter, inside diameter. Right, here's string, pulling some tension right here. Right. Now, part of what makes this work is down at this pivot point, there's a couple of forces. There's the normal force, which I can basically ignore, but there's a friction force. And between this tension force and this friction force, there's now a torque. And if you treat this point at the bottom as the pivot point that's rotating about, it'd be a counterclockwise torque. There you go. And that's the answer. That's it right there. All right. Everybody okay? You good? All right. All right. Oh, where should a 30 Newton weight be placed so that the meter stick will be balanced at the 50 centimeter mark? Okay, so you guys got a minute to solve this. So I got a meter stick balanced at the 50 centimeter mark. I'm hanging a 10 Newton weight at the 20 centimeter mark. Where should I put a 30 Newton weight? Balance that out. I'm gonna draw this one from scratch while you guys are solving that. Okay. So the 10 Newton weight is at the 20 centimeter mark. The fulcrum is at the 50 centimeter mark. Where should you put a 30 Newton weight, which is 3 times the 10 Newton weight, to balance everything out? Oh, look at you guys go! Oh man, this is a good class to record. Yeah, you guys did really good on that. All right. All right, so let's get some numbers on the board. All right, so here's my meter stick, balance at the 50 centimeter mark. That's all good. Right, so I'll do 50 for 50 centimeters. Right, out here at the about 20 centimeters is right about there. I'll put a 10 Newton weight right here. Whoops, here's 20 for 20 centimeters. Here's 0 for 0 centimeters. Now I know this is in my mind. I know torque equals R cross F. Right, so I got this 10 Newton weight right here. I'll go mg equals 10 newtons. Okay. Crossed with, guys, what is this radial distance right here? R equals what? 30 centimeters. Okay. So if I do R cross F, that's torque equals 30 centimeters crossed with 10 newtons. That's 300 Newton centimeters. Okay. Counterclockwise. Here, if I do this right, because isn't that causing counterclockwise like this? Some torque, right? Right. Well, I need a clockwise torque to balance that out. Okay. And guys, if it's 3 times the weight, which it is, it'd be how many times the radial arm? 1/3. Yeah. When 1/3 times 3 balance out, of course, it's also on the other side, right? So what's 1/3 of 30? 10 plus 50. Ah, there's where the 60 is coming from. 60. So I get this radial arm right here of, let's say, R equals 10 centimeters. Right? Cross with, I got a big old weight. That's, I don't think it's going to quite be to scale, but 30 newtons. Right. Now I got torque on the right side is 10 centimeters, because 60 minus 50, crossed with 30 newtons. Ah, there we go. There's 300 Newton centimeters. And that is clockwise right here. So torque left and torque right balance out. Really, one of these should be negative. Maybe the clockwise one is negative. Let's call this negative, negative. All right, so, all right, there you go. You guys there? All right, let's do a little bit more on this one. You guys notice I solved this whole thing relative to this fulcrum as the pivot point? You guys see that? All right, let's do a little extension right here. So make sure you guys get this so far. Guys, right now, this picture, the total torque sums to what? 0. 300 plus negative 300 brings you to 0. That's relative to this fulcrum point, right? What about this point right here? Guys, if I sum the torque about this point right here, does the torque still sum to 0? Yeah, sure does. Think back a couple of weeks ago. It was on a Thursday. I remember how you guys do a seesaw version of a lab. You guys had a spring scale the whole day. In place of this fulcrum here, you guys were just holding the whole thing up with the spring scale. And I had you measure the torque relative to that point, but also what's the torque relative to the end point, which is a completely random point. The torque's still zeroed out. Okay? Guys, what about this point right here? Does the torque sum to 0 about this point right here? Sure does. Yeah, you can pick any point. So, but here's the catch. To pick any point other than the fulcrum, you have to also consider the force at the fulcrum point. Guys, what if you replace the fulcrum point with your finger and you just hold this whole thing up with your finger? How much upward force are you applying to hold the whole thing up? 40 newtons, which kind of goes off the page. So this is definitely not the scale at this point, but I'll call it a normal force of like 40 newtons. Aren't you holding up with 40 newtons right there? Okay. And if the meter stick itself weighs anything, you'd also add that in, maybe like 41, but probably 40, because 10 and 30 down is 40 up. Right. And now you can sum the torque about any point. Right. Whereas the way I did it first, which is probably the most intuitive way anyway, because if I sum the torque about the fulcrum point itself, you could just ignore that normal force, right? It's like pressing on the door hinges of the door. Right. And that's why you normally just solve it that way anyway. All right. Pretty good. Pretty good. I'll look at all these points. Isabel, Peyton, Zach, smiley face, croissant. Croissant's back on fire. Yeah, that opened. In order to increase rotational inertia, ooh, tightrope walker can carry a long stick. True. Look at that. All right. How many of you guys noticed that was actually on your textbook puzzles? Let's see. It's this guy right here. You guys see number 68? Look at this guy and his long stick. Look at that. Or you guys ever try to balance it? You guys hold your arms out like this? Hold your arms out. Right? Guys, if you hold your arms out like this, does that help you balance too? It's the same thing, right? Because guys, what are you changing physically? You're increasing your rotational inertia. Yeah, rotational inertia. That's it. Yeah. Okay. So, like, if you get off balance and you start to fall over, if you have so much rotational inertia, then you can correct yourself before you actually fall. Right? Yeah. So that's what that's about. Tightrope walker right there. Yeah. All right, Isabel, Peyton, Zach, smiley face, croissant. I think this is for the win. You guys ready for the win? All right, for the win. A short pendulum has more rotational inertia than a long pendulum. True or false? Aha! False. Most of you guys got that. Okay. Guys, coming up on Thursday, you'll have a pendulum lab. So that's a great closing question for that reason. Okay. Guys, could this be a pendulum right here? Could this be maybe someone mass? Maybe I hang one of these lab weights as a mass. I got a string with negligible mass and it's just swing, 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 swing. You guys see that pendulum right there? Right? Let's figure this out. Guys, if there was a pendulum that was twice as long, but with the same mass bob on the end, guys, twice as long would be how many times the rotational inertia? 4 times. 4 times. Yeah. Here, guys, let's do some numbers. You guys ready to multiply? Guys, what is 1 times 1 squared? 1. What is 1 times 2 squared? 4. Aha. Aha. Okay. All right, let's see who won Kahoot with the bronze. Zach with the silver, smiley face, and the gold croissant. Yeah. Wait, a smiley face actually a cat in disguise. Let's do your mustache. All right. All right. So I got for you guys. I got a Vsauce video called "Why Don't Any Animals Have Wheels?" Yeah. Close class on this one.
Hey, Vsauce, Michael here, and today we are going to ask a question. Why don't any animals have wheels?